In our previous video, we introduced the idea of the second derivative and talked about how to find it. In this video, we're going to continue on with that concept and see how can I use the second derivative or any additional derivatives to tell us something about the shape of our function and what that's going to mean graphically. So we're going to look at two new concepts here. The first concept is concavity. Concavity is a measure of the curvature of a function. Concavity is the change in the first derivative. So normally when we find first derivative, it's change in x versus change in y, or change in y versus change in x. It's like our slope. But now we're looking at how does our slope change over time? How does our first derivative change over the time? Is the first derivative increasing or decreasing? So the idea here is concavity. Is this going to be opening up or is it going to be curving down? The second idea here is points of inflection. Inflection points are where the concavity changes sign. So from going from concave up to concave down. So maybe we're going something like this. We have some inflection point in the middle, and we have talked about inflection points briefly. Or concave down to concave up. So maybe we're going down and then we're switching to going up. So we're switching from being, concave up to concave down, or concave down to concave up. So we're going from positive to negative or negative to positive. So we set the second derivative to 0 and then solve, and we can use a table to help determine concavity of the function up or down. Let's dive in and see what that looks like. First, with a visual example. So looking at our function here, we're going to be down on this side here, or negative value. So notice if we were to just continue this curve here, it's down. In our top portion here, we have concave up, positive. So we could think if we completed that curve, we'd have a big smiley face there. So that's up. Oops. And in the middle, we have our inflection point, or point of inflection. And what's happening here, this is where concavity changes. All right, so far so good. So we have our two new terms, concavity and inflection point, and we've seen visually and in terms of definition what those mean. Let's see what we can do with them. So going back to our first principles, so to speak, not our literal first principles with limits, but just thinking about conceptually what are derivatives. What does the first derivative tell us graphically about f of x? Well, it tells us our intervals of increase and decrease. So it tells us where our graph is going up and where our graph is going down. Increase of our original function, f of x. We can find local max and min. So we can find points within a region of the graph. We can find where the derivative equals 0, and generally there's going to be a local max or min here. So if f prime x equals 0, there might be a local max or min. Let's take a look at a quick example here. Why might that not always be the case? So if I have f of x equals x cubed, f prime of 0 equals 0. But what does the graph look like here? X, y. The slope of our graph is briefly 0 at that point there. I could have drawn that a little better, but it's not a local max or min. All right, what does the second derivative tell us graphically about f of x? Well, that's where we just learned our two new terms. So it's going to tell us the concavity. Is it curving up or is it curving down? And it's going to give us our possible points of inflection. And inflection are those points where the concavity changes. Let's write a couple statements about what we're looking for here. When the second derivative, when f double prime of x is greater than 0, generally that's going to indicate that f of x is concave up. There's our smiley face. When f double prime x is less than 0, or negative, then our original function f prime x is concave down. There's our sad face. And when f prime of x is equal, or sorry, when f double prime of x is equal to 0, there might be an inflection point. And let's examine our graphs here. So what's happening? Well, we can kind of label these based on their degree or their order. So I'm going to notice right away that my black line here is going to be my second derivative, f double prime x. My red line is going to be my first derivative, f prime x. And my blue line is going to be my f of x. So let's take a look at the values of our second derivative and see what's going on. And I could talk more about my first derivative as well, but we've done that quite a few times already. So what do I notice about my second derivative? I notice that until this point right here, it has a negative value. What does it mean if my second derivative has a negative value? It means my function is concave down. And do we agree with that? Yeah, everywhere here on this function, it's curving downward. What about after this point? What about after the 0 point here? Well, we can see that the value of my second derivative is going to be positive everywhere else here after x equals negative half or whatever, when x is greater than negative half. And so my graph is going to be concave up. It's like my smiley face everywhere else. And what happens when it equals 0? So when my second derivative has a value of 0, I have an inflection point where my graph curves from being concave down. It switches to being concave up. So just a quick overview, quick visualization there. We can see that relationship right away. And then, well, Mr. Strike, you didn't mention like the local max and min there. That's where we would get from the first derivative. Like I said, I kind of glossed over that, but we'll take a look briefly. We noticed that on our original function, if there's a local max or min, those occur when my first derivative here has a value of 0. So those are going to line up there. All right, let's move on. And actually, I lost track of time. That is the end of this note. And so we have successfully seen what the second derivative can tell us about the shape of our graphs. In our next video, we're going to start looking at some examples and what kind of graphs can I examine using first and second derivatives. What kind of application problems can I solve? So if you have any questions about this, if you are live in class, feel free to ask. Or if you're just watching this video on your own later, feel free to pause and go back and review any of the things that I've said, or move on to the second video when you are ready.